real quick look at linear regression. So, police sometimes use shoe prints at crime scenes in order to learn a little bit about the criminals. And so they'll use the shoe print to figure out the foot length and possibly the height. So we're going to look at a linear regression model where we're going to use the shoe print to predict the foot length. And so what I've done here is I've taken in some data and I've put it into StatCrunch. Now this is a trivially small data set, but it will illustrate what we're looking for. And so the idea here is to use the shoe print to predict the foot length. So what I'll do here for linear regression is press Stat, go down to Regression, and we're going to look at simple linear regression. So the input value we're going to use to help make the prediction will be the shoe print, and then we're going to use that to predict the foot length. And so what we'll do here is just press Compute, and it will do some analysis for us. And so the main thing that I'm going to look at initially will just be right up here at the top, simple and regression. So we've got the dependent and independent variable. So foot length is predicted to be 9.11 plus 0.567 times the shoe length in centimeters. It tells us that the sample size is 5, but here it gives us the R and the R squared value. R is the correlation coefficient. It measures the strength and direction of a linear relationship. So typically 0.8278 would be a fairly strong R value, indicating a strong linear relationship. We'll look at that here at the end. R squared is 0.685. That is just the square of this, but it also looks at the percent of the variation that's explained by the regression model. So what I've done here is I've got the model, and so here I've just written in a different order. This is more like your mx plus b that you're used to in algebra. So our predicted foot length would be 0.56755 times x, the shoe print length, plus 9.11 centimeters. So if I were trying to estimate the foot length of someone that left a shoe print of 30 centimeters, I would just plug in 30 for the x, and I would get 26.1 centimeters to be the foot length. And so we would look at R and R squared to give us some measure of how strong that linear relationship is. And so, like I said, usually 0.828 is a fairly strong linear relationship. And so if that's the case, we will have pretty good trust that the output here would be consistent with what we might expect. Remember I said R squared was the percent of variation that we witness in the foot length that's explained by the regression line. And so here I've made a prediction using my regression line that I got from StatCrunch. Now I will note this. Typically this is a strong R value, but if we'll look at something here I've got the Pearson correlation coefficient table. And so for a sample size of 5, I really want an R value that is 0.878 or larger. And so in this case, it's not quite as large as I would like it. So in some books, they would actually say that this is not a very strong linear relationship. And so instead of using the equation to estimate what the foot length is, you might be better off just using the average foot length from the measurements that you were given. And so to kind of reinforce kind of what's going on here, here's a scatter plot, and the line does seem to kind of go through these points, but you don't really have a lot of points to go with. And the line can only be as good as the number of data points that you've got and their reliability. So all said and done, not out of the ordinary, but maybe not as strong as it should be. If you look at the other parameter test, the intercept had a p-value of 0.6 or 2655, and the slope, which is kind of going along with the correlation, the p-value is only 0.0835. Remember, typically we want a p-value that would be 0.05 or less. And so this is close, but maybe not close as we'd like it to be. Well, there you go.